Okay, so this is your lecture number 4, and in this lecture, before this lecture, what we have done till now, we have done some of the formulas for the Laplace transform of various functions, and in addition, we did two formulas for sine and cosine hyperbolic functions, and one formula for the Laplace of x raised to power n, where n was a real number, and the Laplace comes in the form of gamma function, gamma n plus 1 upon p raised to power n plus 1. So it was the Laplace transform of some function. After that, we shift to some of the properties that we can use while solving the problems of Laplace transform. And first property was first shifting property, in which fx is multiplied with your EAX. So in that case, you get the Laplace in the form of Laplace transform in the form of fp minus a. That is, you just need to find the Laplace of fx. So Laplace of fx you usually get equals to fp. We represent it by fp, and whatever it is fp, you replace using first shifting property fp by p minus a. That is, in fp replace p by p minus a. So this is how the first shifting property works. After this, the second property was of differentiation of Laplace transform, in which fx is multiplied by x, and in that case again you get the Laplace transform as a minus first derivative of fp. Fp again is the Laplace of fx, and in general this property says that Laplace of x raised to power n dot fx is minus 1 raised to power n dot nth derivative of fp. And finally, we did the integration of Laplace transform, the property number 3, where your Laplace, in which the Laplace we found for the function when fx is divided by x. Here the function fx is divided by x, so in that case we get the Laplace transform equals to p to infinity fp dp, and fp again is the Laplace transform of fx. So main thing in all of these properties is that you actually have to find the Laplace of fx and then change or manipulate it according to the property. So this is what we have done till now. Okay, so now after this one, what we will do next, we are starting your inverse Laplace transform. So next is your inverse Laplace transform. So this is the inverse of the Laplace transform that we have done. Remember that we have the Laplace of fx, we define it as 0 to infinity e raised to power minus fx dx p greater than c, and we represent the product or term, whatever it comes, in that form of some function of p, and this is what we say the Laplace transform fp, and here it is the transformation. L is the transformation, Laplace transformation. So now he says, from here he says Laplace inverse of fp, here we take it in the square brackets, is equals to fx. So if you have Laplace of fx is equals to fp, if you have something like this that we were doing, so then the Laplace inverse, we take Laplace or L this side, so this is Laplace inverse of fp is equals to fx. That is, here this Laplace inverse, it is called the inverse Laplace transformation. Similar to Laplace transformation, it is the inverse Laplace transformation, and here it is your inverse Laplace transform. It is the inverse Laplace transform. So that is basically the opposite of what you have done in the Laplace transform and transformation. So here in the inverse Laplace transformation, it is a operation again which when applied on fp, will give you function fx, and this fx so obtained will be inverse Laplace transform of fp. So now, similar to what we have done in case of your Laplace transform and transformation, here again we have some formulas on the same lines that we did for Laplace transform and Laplace transformation. The formulas are similar. Remember that Laplace of k, or let me write it as your z1, constant 1, let me write it as 1. It was 1 upon p. So this implies Laplace inverse of 1 upon p is equals to 1. Constant is equals to 1 by p. Remember, we have Laplace of x is equals to 1 upon p square. So this implies Laplace inverse of 1 upon p square, 1 upon p square is equals to your x. So this is your 1 upon x square, 1 upon p square is equals to x. Similarly, in general, similarly, Laplace of x raised to power n, we have done this equals to, we have the two forms. One is your n factorial upon p raised to power n plus 1, n is positive integer, and one of the form we did was gamma n plus 1 p n plus 1, where n is greater than minus 1 and n is in case a real number. So we have the formula for this. So using this, you can write Laplace inverse of n factorial upon p n plus 1 is equals to x raised to power n, n is your positive integer, n is positive integer, and this is Laplace inverse of gamma n plus 1 upon p n plus 1 is equals to, again, x raised to power n, however n is greater than minus 1 and n a real number. So this is the formula for your Laplace inverse that you get in case the function is x raised to power n and n is positive integer and a real number. Then you have your Laplace, EAX, that was your 1 upon p minus a. So Laplace inverse of 1 upon p minus a is directly e raised to power x. Similarly, you did it for sin x and cos ax. So Laplace of your sin ax, it was a upon p square minus a square. So p square plus a square, minus is for hyperbolic. So Laplace inverse of a upon p square plus a square is equals to sin ax. Similarly, Laplace of your cos ax is equals to p upon p square plus a square. So Laplace inverse of p upon p square plus a square is equals to cos ax. So similarly, these are the formulas that we can derive from the formulas of Laplace transform that we did earlier. And two more formulas for hyperbolic function. You can also write that Laplace inverse of a upon p square minus a square, it is sin hyperbolic ax, and Laplace inverse of p upon p square minus a square is your cos hyperbolic ax. So this is the formulas that we are going to use while solving the questions of inverse. So now, what is the use of doing the inverse of Laplace transform? The reason is that while we will be applying the Laplace transform to find the solution of a differential equation, that while we will be studying the application of Laplace transform in solving the differential equation, there it is going to be used, the concept of inverse Laplace transform, because otherwise without that we will not be able to solve the differential equation. So we need the inverse of Laplace transform also. So here, after using these formulas, let us see how we can use these formulas of Laplace inverse in various questions. So let us first question we consider Laplace inverse 2p plus 5 p square plus 25. So this is what you have to find. Now in the question of inverse, you have to think opposite what we were doing in the case of Laplace transform and transformation. So basically he is asking you, he is giving you fp, he is giving you fp, fx you have to find, and fp he is giving you, that is fp is 2 5 plus 5 p square plus 25. So this is what he has given, and you have to find fx. Fp is given. So let me write it more precisely so that we can work it out properly. So using the property of linearity, I can write it as 2 times p upon p square plus 25 plus this is 5 or Laplace inverse 5 upon p square plus 25. So using the property of linearity, I wrote it like this one. Now you can see in one of the case I took the constant outside, in one of the other case I retain the constant inside. So it depends upon the user. He can just take it outside the Laplace inverse or keep it inside the Laplace inverse. Now the thing is, while we are working for the questions of Laplace inverse, there we have to see that the Laplace inverse of fp that we are working with, then which formula it correlates with. So if you can see this fp, p upon p square plus 25, it correlates with the formula of your cos x. I'm just not saying exactly what cos it is, but since it is p square plus 25, so this is going to correlate with the formula of the cos, and this 5 upon p square plus 25, it correlates with the formula of sin x. So let us work out one by one. Let me take this first. Since this correlates with the formula of sine, and I know that sine Laplace of sine 5x, because we have done the question in this form. So let me start with the form the way we did it in the previous lecture. So sine 5x, we know it is 5 upon p square plus 25, and that is, you can see, that is what he is asking you. So this implies Laplace inverse of 5 upon p square plus 25 is equals to sine 5x. So you got the, say this is equation number 1, you got Laplace inverse for sine 5x. Now other is your p upon p square plus 25. Here it is, other is, and we have just pointed it out that it correlates with the Laplace of cos x. So let me write, since Laplace of cos 5x, because in the denominator it is p square plus 25, so it is p upon p square plus 25. So this implies Laplace inverse of p upon p square plus 25 that he was asking, and that is why in this case I took the two constant outside. Otherwise, if it is there, that is not going to create any problem. So this is cos 5x 3. Put 2 and 3 back in the question. In 1 we get this is equation number 1. So we get Laplace inverse of the given function, that was 2p plus 5 upon p square plus 25 as 2 times cos 5x, because here it is Laplace inverse 2 times Laplace inverse p upon p square 25, that is cos 5x, plus sin 5x. So this is fx, this is fx. This was Laplace inverse fp, which he has given us to solve. So this is how we solve these type of questions of your inverse. Now coming to another example. So clearly, at least in this question, we can correlate the fp that was given to us in a very simple way. We did not have to do any type of manipulation, but in other questions there it is not, we will not be able to correlate the formulas of Laplace directly, but we need to manipulate the given fp. For an example, consider this Laplace inverse. So again fp here is 3 upon p square plus 2p. So now you can see here this formula, just by looking at the fp, you can't say that the Laplace of this fx is equals to this fp. It does not correlate with this fp in the present form, at least. So what we do, we manipulate it like 3 p square plus 2p, you can take 3 outside, constant, and then if we take p common, it is p plus 2. And again, now we can what we can do, we can just here do partial fractions, and using partial fraction we will get this one divided by 2. So we use partial fraction. This is one of the important tool while solving the problems of Laplace inverse. So you know very well, I'm not going in the depth of Laplace in partial fraction. So this is ap plus b p plus 2. So a in this case will come out to be 1 by 2 and b will come out to minus 1 by 2. So we get this form. And now you can see these fp, we know whose Laplace inverse they are, or we know the function fx whose Laplace if we take, then we will get this 1 by p or 1 by p plus 2. So let me just sort it out more properly. So this is Laplace inverse 1 upon p minus Laplace inverse 1 upon p plus 2. So this is, now I am not writing it separately, because if we know the Laplace inverse of the given form, we can write the formula directly. So this is for the constant 1. We know Laplace of 1 is 1 by p, and Laplace inverse of 1 upon p plus 2. We know that Laplace of eax is 1 upon p minus a. So here it is e raised to power minus 2x. So Laplace of e raised to minus 2x will be 1 upon p plus 2. So here is the form solution that you will get in this question. So here there was a manipulation in the actual given fp. You were not able to identify the fx, so we need to manipulate the fp, and we did partial fraction, and after partial fraction we got the very forms where we can correlate the Laplace inverse with the formula of constant and e raised to power minus 2x. Okay, so this was the second question. Now let me come to your example number 3 regarding the properties of your inverse Laplace transform. Third is find inverse Laplace transform of your fp given to be p 3 by 2. So this is the next question. Now you can see here, in this case the fp whose Laplace inverse we have to found is in the form of your p raised to power 3 by 2. P raised to power is some real number. 3 by 2 is a real number, and we know very well that Laplace of x raised to power n is p raised to gamma, this is gamma n plus 1 upon p n plus 1, n greater than minus 1 and an real number. So whenever we have p raised to power a real number, when we have Laplace inverse of 1 upon p raised to power real number, this formula that contains the gamma function, the use of gamma function, that is going to be used in one or other way. So using this formula, since we have p raised to power 3 by 2, so we can write Laplace of x raised to power 1 by 2 is gamma 1 by 2 plus 1 using the above formula, p 1 by 2 plus 1. Why I took x raised to power 1 by 2? Because that's Laplace will make p raised to power 3 by 2. So this is, now this is gamma 1 by 2, let me write it as such, and p 3 by 2. Now we use the property gamma n plus 1 is equals to n gamma n when n is greater than 0 and real number. So this one gamma 1 by 2 plus 1 will become 1 by 2 gamma 1 by 2 p 3 by 2. Again we know the property gamma 1 by 2 is equals to under root pi. So this becomes under root pi 2 p raised to power 3 by 2. So this is Laplace of x 1 by 2. So in the question what he's asking for the Laplace inverse of p 3 by 2. This is what he's asking in the question. So for that I need to adjust these constant, and I took it here 2 raised to power x 1 by 2, 2 I took here, and under root pi here. So this gives me 1 upon p 3 by 2. So implies Laplace inverse of 1 upon p 3 by 2 is equals to, this is 2 under root x under root pi, or 2 under root x upon pi. So this is what your solution of the given problem is. So here the gamma function was used as the denominator, p raised to power n. N here is 3 by 2, that is real number. So here the gamma function was used. So this is how we can use the various formulas of your Laplace transform to solve the problems of inverse Laplace transform. Next we come to, remember that after doing the Laplace transform of various functions, we did three properties as we mentioned in the beginning: first shifting property, then the differentiation of Laplace transform, and your integration of Laplace transform. So similar in this inverse Laplace transform, we will be doing the inverse of certain properties that are widely used in the problems of Laplace inverse. So first is your first property after these formulas for inverse Laplace transform is the inverse Laplace transform of property 1. Property 1 was your first shifting property. Property 1 or first shifting property. That is the inverse Laplace transform of first shifting property. Since you know very well that since Laplace of, or let me write first, if Laplace of fx is equals to fp, if I assume that Laplace of your fx is equals to fp, if this exists, and then by first shifting property we have Laplace of eax dot fx is equals to fp minus a. This is the your relation for your first shifting property. So inverse says that Laplace inverse of fp minus a is equals to eax dot fx. So this is the inverse of your first shifting property, that Laplace inverse of fp minus a is equals to eax dot fx. So now what will be happening in these type of question, you can see in the last question what we did when we were solving the questions related to the formulas, various formulas of Laplace inverse. We tried to find the fx with which the given form of fp is correlated. Sometimes that can be identified easily, or sometimes we have to do some manipulation. Now in the problems of your inverse Laplace transform related to your first shifting property, here there is some shifting of p, that is you will get the fp not in the form the function Laplace exists, but in the form that there is some shifting in the p. How, what is that? So let me take an example and see what we are talking about, or how we identify that. Here in the question the first shifting property is going to be used, inverse of first shifting property is going to be used. So question is find Laplace inverse fp, where fp is 24 p plus 2 raised to power 5 plus 2 upon p plus 2 plus 5 upon p plus 2 ka whole square. So now in this question you can see I need to find the Laplace inverse of fp. So let me use the property of linearity and write it like f plus 2 5 Laplace inverse 2 upon p plus 2 Laplace inverse 5 upon p plus 2 ka whole square. I am not taking outside the constants, okay, I will leave it as such, and then we will see what we will do with these constants. Now let us start with this first Laplace inverse. This is Laplace inverse 24 plus p upon p plus 2 raised to power 5. This is what now we have to find. Say we take it particularly separately. Now in this question you can see the fp given here does not correlate with any of the form. If even you can skip 24, you can just see p plus 2 raised to power 5, because that is what going to correlate with the Laplace of some function. But it is not correlating with any Laplace of any function. However, if I take out this plus 2 from here, if I take out plus 2 from here, I will be left with 1 upon p raised to power 5, and I know whose Laplace transform is this one. I know this is related to the Laplace transform of x raised to power 4. So now then, using the first shifting property, I can reach up to here. So this is how we identify where to use Laplace inverse of first shifting property. So if I remove plus 2 from here, I got this fp, and this correlates with x raised to power 4, and hence in this way I can use first shifting property. How? So from here I identified that it is related to the Laplace of x raised to power 4. So this is 4 factorial upon p raised to power 5. That is okay. Now I will use first shifting property, because ultimately I have to go to this one. I have to find the Laplace inverse of this function. Constant 24, that can be adjusted. So using first shifting property, I know Laplace, if I take e raised to power minus e2x dot x4, the Laplace of this is this one, then the Laplace of e minus 2x dot x raised to power 4, by first shifting property, p will be replaced by p plus 2, that is this one. So 24 upon p plus 2 raised to power 25. So this is how I got the Laplace inverse. So that Laplace inverse of 24 upon p plus 2 raised to power 5 is equals to e minus 2x dot x raised to power 4. So this is your equation number 2. This is equation 1, this is equation number 2. The Laplace inverse of 24 upon p plus 2 raised to power 25 raised to power 5. Now second was your Laplace inverse of 2 upon p plus 2. Second term was this one. Now you can see this is the direct, this is the direct formula, Laplace of ex. Even I can avoid using the first shifting property here. I can directly write it as 2 times Laplace inverse of 1 upon p plus 2, and I know very well that Laplace of e minus 2x is 1 upon p plus 2. So this is 2 times e raised to power minus 2x. So this is 3. The Laplace inverse of 2 upon p plus Laplace inverse of 2 upon p plus 2. This is how we can use the formula. From here I wrote the formula as such. Need not to do any type of other calculation here. And the third was Laplace inverse of 5 upon p plus 2 ka whole square. So clearly in this case you can see again the term is 1 upon p plus 2 ka whole square, neglecting the constant, and this relates with 1 upon p square. If plus 2, if you remove, then it is 1 upon p square, and this relates with the Laplace of x. So since we know that Laplace of x is 1 upon p square, then your Laplace of e raised to power minus 2x dot x is 1 upon p plus 2 ka whole square. So this is Laplace of 5 dot x dot e raised to power minus 2x. Just to adjust that constant, I got this one. So implies Laplace inverse of 5 p plus 2 ka whole square is 5x e raised to power minus 2x. So this implies this is the Laplace inverse third that I got for the given question. So put 2, this is equation number 4, sorry, this is equation number 4. Put 2, 3 and 4 in 1, we get the Laplace inverse of fp is equals to, so we got here the formula as this one. For the first term we got e minus 2x x raised to power 4. So here it is e raised to minus 2x x raised to power 4. Then for the second term we got 2 times e raised to minus 2x, and for the third term we got e minus 2x dot x. So I can take e raised to minus 2x common. I will get x4 plus 5x plus 2. So this is the required fx that is asking for, Laplace transform, inverse Laplace transform. So here fx is inverse Laplace transform of the given function fp. So this is how we used to solve the questions of first shifting property. There we have to identify that after removing that shifting, which formula that Laplace inverse of fp correlate with. So example 2, the Laplace inverse of p square minus 4p plus 8. Say you have to find the Laplace inverse of this one. So in these type of problems, you can see here again, in the previous problems, you can see just by looking at the given fp, you can then shift a or plus a or minus a in fp, and you can identify the Laplace inverse or the Laplace of function whose Laplace inverse it correlates with. But in these questions, type of question, we have to do a bit manipulation in the beginning to reach up to that stage. Here we can see that there is some shifting of plus a or minus a in the formula of fp. So here, first of all, here in type of question, we need to make perfect square. So here you can see I can make the perfect square here as p minus 2 ka whole square plus 4. Now I can write this more precisely so as that this correlates with my one of the forms. This is, now you can see this is the formula. In the present form it is not again correlating with earlier. In the earlier example we start up from here, that we got the form where the shifting of p in fp has been done by plus a, p minus a, or p plus a, something like that. Now in this form we have to do some manipulation, and now we reached up to here. Now here you can see in this form, if I remove minus 2, I will get 1 upon p square plus 2 square, and that is the Laplace inverse or Laplace of sine x. It correlates with the Laplace of sine x. So I got a hint that it is going to be related with the Laplace of sine x. So let me start with sine 2x, because this is p square plus 2 square. So this is 2 upon p square plus 4. That is okay. And now to get this form I need to use first shifting property. E raised to power 2x dot sine 2x is your 2 upon p minus 2 ka whole square plus 4. So this implies the question that he is asking, that is asking Laplace inverse of 1 upon p minus 2 ka whole square plus 4. The constant 2 I adjust it with right hand side. So this is sine 2x. This is the solution of the given problem. This is gx that is asking for. This 2 I just skipped one step, I just take it there and I wrote it like this one. So this is how we can solve these type of problem, where we have to initially manipulate a bit the given fp, then it comes in the form where we can correlate it with the first shifting property of some function. Now in the last there is another example. Yes, here it is. So here you have your find inverse Laplace transform of fp is equals to 1 upon p raised to power 3 by 2. So its Laplace inverse we have to find, and this is your question. Okay, sorry, I think we did this question earlier. I just missed the question. Just hold on. This is example 2, and yes, here it is. Just hold on, just I missed the statement. The statement is 1 upon p plus 1 5 by 2. Yes, so here it is the formula that we are now going to, sorry, question that we are going to do, it is p plus 1 raised to power 5 by 2. So again, this type of problem we have done earlier also, but here the formula or fp here is not as simple as was in the previous question. So again, in the denominator of fp you have 5 by 2, you have a real number. So the formula of Laplace x raised to power n, and you know the x, Laplace of x 3 by 2, I am now doing it directly, it is 3 by 2 plus 1, and now in the denominator I will get 3 by 2 plus 1, that is 5 by 2. Again, using the property, I got 3 by 2 gamma 3 by 2, this is p 5 by 2. Using the property gamma n plus 1 is equals to n gamma n, where n is positive. So this 3 by 2 gamma can be written as your 1 by 2 plus 1. This is p 5 by 2. So I got this 3 by 2 dot 1 by 2 gamma 1 by 2. Again, using the property of this one, again here I got this thing, and then finally you know that this gamma 1 by 2 is equals to under root pi. So this is 3 under root pi upon 4 p 5 by 2. So this is Laplace of x 3 by 2. Now since why we are taking with x 3 by 2, because as we did in the earlier examples, in this question same, if I remove plus 1 from here, I got p 5 by 2, and I know the Laplace of this Laplace inverse of this function, that the Laplace of fx is x raised to power n or x raised to power 3 by 2, from where I will get this inverse Laplace transform, or is this inverse. So first I am targeting 1 upon p 5 by 2, its Laplace inverse. So from here I got this thing, this is what I have got now. But in the question it is p plus 1, there is a shifting, p has been replaced by p plus 1. So now will come into play the first shifting property, that is Laplace dot e raised to power, it was p plus 1, so it is e minus x 3 by 2, because all other things, these constant, they can be adjusted. So this is 1 upon p plus 1 5 by 2. Here this is the term of p, that will be now here p replaced by p plus 1. So this implies, now adjusting the constant, you have 4 e raised to power minus x 3 by 2 3 under root 5 is equals to 1 upon p plus 1 5 by 2. So this is how we got up to the thing fp where we want to, and this implies Laplace inverse of 1 upon p plus 1 5 by 2 is equals to 4 e minus x 3 by 2 3 under root 5. So here it is. So this completes the question for your this type of problems when you have your the x raised to power n, where n is a real number, and in addition you are having the use of first shifting property. So with this I now close this lecture, and in the next lecture we will be doing the inverse of some other properties. And with this, let me close the lecture. Thank you. Thanks a lot.